Hey everybody. מבחינת אנגלית, I was asked to give this in English. You could ask questions in Hebrew. Throughout the talk, I will translate them to English and answer, okay? So just תזרמו איתי. Please sit down. So, I'm going to talk to you about side channel attacks, but a very new setting for side channel attacks, which really has dramatic implications on what we need to think about side channel attacks and what it means for us. So, before I do that, I'd like to tell you about So before that, I'd like to tell you about something very important, which is called the Master's Degree in Cyberspace Security in Ben-Gurion. It's a new program. We are just having our first year of graduates this year, and it's built just for you, okay? So whatever you feel about security, obviously you love security, and if you want to invest a bit in it and show how much you love it, take the next step, take an advanced degree. So if you want to keep your job, studies are 1 day a week in the afternoon, okay? So you can do it while studying. If you're saying, I love it so much, I want to dive in and be a researcher, first of all, I would really appreciate it. I have a lot of interesting stuff to do. We have very generous conditions for people who join our research group as full-time researchers. And it's very close to Azrieli, 62 minutes by train. I bet that I can reach there faster than you can reach Ramat HaChayal. Registration for this year is still open, so if you go outside to Bat-El, she's on the booth on the other side of this wall, get details from her. You can start studying 2 weeks from now. It's an amazing opportunity. This degree is for you guys. Please ask about it, learn about it, and join us in Ben-Gurion. So I'm just going to talk about some of the stuff we do in Ben-Gurion. Maybe that will make you appreciate this degree program even more. So, before I start, I want a little calibration, just to understand the people here. Please raise your hand if you understand what's going on this slide. Okay. Okay. 35%. Please raise your hand if you would feel comfortable going up on stage and explaining the slide instead of me. Anybody from Intel here? Okay. So, side channel attacks. They are the most powerful method of attack available right now. If the KGB wants to attack the American embassy in Moscow, what do they use? What do they send? Maybe like mysterious, beautiful agents, but most probably they're going to use side channel attacks. What is side channel attack? So let's assume we have some kind of secure functionality, some kind of secure system, and this system has inside it a secret. And it uses the secret to turn inputs and outputs. The most common interpretation of this is, of course, this is an encryption device, and the secret is a secret key, and in comes plain text and out comes ciphertext. But we can also think about any system which has a secret in its belly and provides CIA, confidentiality and integrity. This could be TCP sequence number. This could be session cookies. This could even be your Facebook friends or your browsing history. Okay? So there is a secret. We want to get the secret out of the system. What do? If we're really clever, like Helen and her team, we're going to do some cryptanalysis stuff and rainbow tables and all that. If we're not, if we're engineers and we love to cheat all day, what we're going to do instead is side channel attacks. And side channel attacks build on the realization that a system actually has another output, which is called its physical artifacts. So if a system is doing a computation, a calculation, it's not just going to give us this output, it's going to do other stuff. It's going to consume power, it's going to take some time, it's going to access memory, it's going to access resources. So side channel attack is the art of looking at these emanations and learning from them about what the system is doing. And it's a very, very powerful attack method. So how powerful it is? Here are a few systems which were attacked using side channel attacks, and we know about, of course. Okay, so this is a immobilizer. You can steal BMWs with side channel attacks. This is secure payment systems, IP protection for hardware devices, firmware protection. Xbox 360 is firmware was broken using side channel attacks. Very interesting story. And this is called the Bell 131B2. That's actually an encryption device used in World War II. It's the most high security encryption method called OTP, Machap in Hebrew, and it was broken using side channel attacks. So this is a very, very powerful system. Other stuff which was broken with side channel attacks: RSA, DES, AES, Bitcoin, keylogging, you name it. So it's a very, very powerful attack system, and of course the natural question you're asking yourselves is, why didn't the sky fall on our heads? Right? We're still happily using AES and RSA and Bitcoin, and somehow the world is still surviving. We're not trading pelts with each other and pieces of shells and stones. We still have our world. So the thing is that side channel attacks have a very serious drawback, or a very serious problem, which makes them less potent than sometimes people want you to believe. The problem is the problem of the attack model. Okay, so let's take a look at, we actually had a side channel attack today, okay? Timing attack. The problem with side channel attacks is that they require something which is called close proximity. The attacker has to be close in some way to the device under attack. So what does close proximity mean? It really depends on the application. So close proximity could mean I have the device in my hand. It could mean I have an antenna which is like 3 feet away from the device, 1 meter away from the device. It could mean that I've opened the device and actually installed some measurement probes inside it. So in the case of cache attacks, as we're going to talk about today, the attack model assumes that I can run binary code on the same hardware running as the device under test. Now that sounds really ridiculous. Why should this even exist? Why should I even assume this is an attack? So what is one environment when the attacker and the victim can run binary code on the same machine? What is this environment? VM and? Yeah, clouds, exactly. Amazon has a big cloud, and they don't really tell you who are you being co-located with. This is why it's so cheap. So everybody gets the same infrastructure, and the attacker and the victim are happily sharing the same hardware. So, okay, so in cloud, you can say that you can run binary code together, but most of us are not in the cloud yet. We have our own personal computers, and this attack model doesn't really make sense for the computers we use every day, for browsing the web, for doing commerce, for our phones, and so on. So, security designers, who are part of an ecosystem, they're part of an organization that writes products, they say there is no close proximity in our system. Therefore, there is no risk of side channel attacks. Therefore, we're not going to spend the time and the money and the resources to add some countermeasures to side channel to protect ourselves against side channel attacks. This is the situation today. And by the way, there was in 2009 an attack was found on Amazon. They said, "Hey, you're vulnerable to side channel attacks," and they said, "Right, but nobody's really going to do it anyway." So, and we're like 7 years later, and nobody actually did a side channel attack because the attack model is so restrictive. So, what I'm going to show you today is something which kind of improves on this. I mean, depending on which side you're looking from. And we're going to write a side channel attack that lives on a web page. Okay? So the definition of close proximity is very, very relaxed here. So all I need to do to get my victim to perform this attack is get my victim to view a web page. Now, how easy it is for an attacker to cause a victim to view a web page? Very easy. How do you do it? Do you know? Email is, no, I don't have time to send email. Social media, I don't have time. I don't have any friends. That's why I'm in the university. What? Okay, so who speaks here Russian? And you can kind of translate to us what this says here. So, hello. We have 8,000 to 9,000 visitors from US and Canada looking for adult entertainment and business. And you can deliver iframes to them for $380. This is what they call pay-per-view. This is affiliate networking. Like ad networks, these are called content networks. So some of them are really, really shady and forums in Russian with black background. Some of them are really legitimate ad networks and ad markets and so on. So basically you can spend a few dollars and get this attack to millions of people. So instead of the traditional imagination of a side channel attack where somebody goes to this high sensitivity target with an antenna, or I don't know, with a drone or whatever, this is something you can just cheaply throughout to millions of computers. So this is a very unique thing about this attack. And another thing we do, so usually we talk about side channel attacks, usually the name of the game is they have a very secure server, and the server has a key, so you're going to steal the key. So in this work we showed that you don't get the key, you can get other stuff, which is very interesting. In our case, we're going to use side channel attacks to compromise privacy. And what we're going to do is take a user who is using Tor browser and find out what this user is going to, which website he's going to over the Tor network. Okay, so if this is interesting to you, please join our research group. So I'm kind of a one-track mind today. So a little bit about cache. I really don't have much time to go on to it, but the basic problem is CPUs are very, very fast, and RAM is not so fast. RAM is actually quite slow. So if the CPU would have to take all of the instructions and code it needs from the RAM all day, it will spend most of its time waiting for RAM, and it won't run as fast as we expect it to. So the very clever designers in Intel and other companies do something called the cache hierarchy. So what they do is they take pieces of memory which is very, very, very fast and place it really close to the CPU's cores, actually physically on the same piece of silicon. And then they take a little piece of memory which is a little larger and a little slower and place it a little closer. Then you go level 1, level 2, level 3, level 4. And if you can't find whatever you need in the cache memory, you just go to the RAM and you have to wait. And what's really nice is that usually programs do the same thing over and over again. So most of the time, the cache really satisfies the CPU and all the cores are running in full speed. So this is a fourth generation Core i7 computer, and it has 4 cores. You see it's a quad core. And there are this little red and purple caches are the level 1 cache. They're really, really fast. And there are the level 2 caches which are a little slower. They're the blue ones. And the last level cache, it's really large, 6 megabytes. It's the slowest of them, but it's really still a lot faster. It's like 40 times faster than RAM. So what happens is that whenever the CPU needs to get something from memory, it has a piece of hardware called the memory management unit. The memory management unit looks for this piece of memory in the cache. If it finds it, sababa. If not, there's something called the cache miss. We really hate that this happens, and there's a cache miss. The MMU goes to the DRAM, everybody has to wait for it to happen, and then it takes this piece of memory and it puts it in the cache. Obviously the cache is smaller than the entire memory. So the memory management unit does something called eviction. So it throws away one of the items which is already in the cache and puts this new item inside. So there is cache miss and cache replacement. If something is thrown out of the cache, you replace it. And now there is something called associativity. The idea is that this, especially the last level cache, the 6 megabyte cache, is so large that the MMU doesn't have time to search the entire 6 megabytes every time the CPU needs memory. So what happens is, this memory, the 6 megabytes of memory is sliced into 8,000 sets, small pieces of the cache, and each address in physical memory gets a single set it goes into. So we're actually dividing physical memory into 8,000 pieces, and each one of these pieces is small. There's, I think, 12 to 16 lines in each set, which go into this cache. So what this basically means is that there is for each set in the cache, you don't get the entire memory competing for it, only a small proportion of the physical memory. And the last thing I want to talk about is virtual memory. Everybody knows that computers, user space programs, don't actually get to touch the physical addresses. Even if you look at the lowest level of machine language code, they don't know the physical addresses. They use virtual memory, and this memory management unit, again, magically changes these virtual addresses into physical addresses. So, just to put this in our heads for a second. If you need to learn more about this, you can look at the paper and so on. So, here's a little piece of information about this fourth generation Intel CPU. You see it has a level 1 cache, 4 times 32 kilobytes, and a level 2 cache, which is 256 kilobytes, and a level 3 cache, which is 12-way set associative, which means that each set in the cache, there are 8,000 sets, each set gets only 12 entries, each set only has 12 entries at the same time. Okay, so I really don't expect you to understand what cache is after this very short explanation, but maybe you want to learn about more, you can find out yourselves. So, how do you do a cache attack? This is a side channel attack. What you do is you take a set in memory, and then you monitor this set, and you see what's going on in the set. Is this set being accessed by the victim or not? And the assumption is that maybe, for example, there is an if-else statement in the victim's code, and if it takes one branch of the if, it goes to one set. If it takes the other branch of the if, it goes to the other set. If you see if the set is being accessed, you know a little bit about the internal state of the victim, and you can build an entire attack on this thing. So I find the set, and I monitor it, and I see what's going on with the set. And it was actually discovered for starting in 1992, and it's been used to break a lot of stuff. AES, RSA, Bitcoin, and so on. I'm going to show you a very short demonstration of the attack method I'm going to use, which is called prime and probe. Okay? So this is prime and probe. This is the attacker's memory. Virtual memory, of course. The attacker doesn't know physical memory. And this is the cache. Okay? I have a couple of sets, and I think that set 1 is shared with my victim. So first of all, what I'm going to do is find something called an eviction set, which is a piece of my memory which all goes to the same set. Obviously, there's a little trick in doing this. You have to do a little reverse engineering, but it's okay. We know how to do this. I found a bunch of virtual memory addresses. Every time I access one of these virtual memory addresses, it goes into the same set in the cache. And if I access all of them in a row, I take control over the entire cache set. Everything in this cache set is the attacker's addresses. And now, once I've taken over this cache set, I'm going to wait a little while and let the victim do its stuff. So now the victim is running, and maybe or maybe not, it's accessing this cache set. And obviously it's going to throw out one of my entries because there's only so much space in the cache, and it's going to take over this cache set itself. So now I know that the victim finished doing its stuff, and the next thing I do is probing. So what I'm going to do is access my memory addresses again and see how fast it takes. So if the victim accessed the memory and threw out something from our cache, will my access be fast or slow? Who says slow? Who says slow? Raise your hand. Who says fast? Don't raise your hand. Right. If the victim ran something and threw something from my cache, my access will be slow. How slow? 40 nanoseconds slower. Okay? For a single cache miss. If it didn't do that, well, my access will be fast, and then I can learn something about what the attacker is doing. So this is prime and probe attack. And of course, there I accessed again, and now I go from the cache. So now the idea is to do this in JavaScript. I have to find out physical memory addresses which go into the same cache set, and I have to measure with 40 nanosecond resolution, and I have to do this in JavaScript. So obviously this is a little challenging, right? Because JavaScript doesn't actually compile to binary. JavaScript is a scripting language. I deliver script to my browser. The browser doesn't even have to compile it. Sometimes it compiles it, sometimes it doesn't compile it, right? And of course, JavaScript doesn't even have pointers. JavaScript doesn't have memory allocation. Of course, the JavaScript doesn't have syscall or something. And the timing API they have to use for JavaScript. Why should I get 40 nanosecond resolution in JavaScript? I mean, this is for, for buttons, right? For animations. So fortunately for me, there are some very nice new APIs which are coming in, really coming in after the past few years. And surprisingly, it's possible to do very high resolution measurements in JavaScript and very high speed memory accesses in JavaScript. So if you want to find out how we do it, please, I wrote a paper, do me a favor, read it. It's on the website and so on. So, let's take a look at what happens. I did the attack, and now I'm going to show you a real-time, actually it's a recording of a real-time view of what memory accesses look like on a quad-core Mac running Safari, okay? And this measurement was done in JavaScript, okay? So, x-axis is time, the y-axis is pieces of the cache, and you see here that most of the time the cache is really idle, nothing is going on, and once in a while you see these dots. These dots are when somebody has been accessing the cache. Not my process necessarily, could be the operating system, could be another virtual machine, could be the hypervisor. I can see it from JavaScript. So I see this line up there. This line is probably a variable because it's the same place all the time. And these lines, these horizontal lines are probably functions, right? Because functions are a lot of memory on after the other. So, and this isn't JavaScript, this is ridiculous. Okay, I can see everything going on in the computer. I can do measurements from a VM and measure the host. And of course, this is what the memory is doing normally, but if I write a program that accesses memory in a funny way, I can also collect this with the memory gun. This is another one I recorded. So I wrote, you can't really see this. You can see this. So I wrote a piece of code in Chrome which allocates a memory and just iterates over it in a certain pattern, and then I measured it using this method, and you can communicate between two processes using this silly way. So this is really, really cool. But cool isn't enough in our business. I need to actually attack something. So let's attack. So as I said, side-channel attacks have been going around. Oh, I don't want to show you that yet. They've been going around for a while now. And usually they've been attacking virtual machine instances because it's a cache attack. It's running in the cloud. It's doing some kind of back-end functionality, maybe generating random numbers or encrypting or signing or something. And of course, it's not connected to anything interactive. It's just running in the cloud. And that's why most attacks go after the keys. That's what you have there. So in our case, actually, it's a very different setting. So the victim is, by definition, a computer which is connected to the web, right? This is why the attack works. And the user is going to use the computer to do whatever he likes to do, browse the internet, enter passwords, and there's a lot of secret information in the interaction between the user and the computer, actually. The mouse movements, the keystrokes, even the automatic brightness control. Don't know if you noticed that, if you move in front of the computer, the screen goes a little darker. So actually, when we were waving our hand in front of the sensor, we got measurements in JavaScript. It's really ridiculous. So the attack I'm going to show is going to target the victim's privacy and not getting any keys. It's still a little scary. So this is how the attack looks like. There is somebody using a normal browser, let's say Safari or Firefox, and they've been forced to view our attack webpage. This attack is running in the background. And also they're running a very sensitive browser because they have something really sensitive to do. There's a little website they want to go to, and they don't really want anybody to know about it, so they either start incognito mode or private browsing, or they even start something called a Tor browser, which is a super secure version of Firefox, which works over the Tor network. So this is really, really a sensitive browser. It's a different executable, okay? A different process, could be even a different user. But still, everybody meets together in the CPU. Now, so I'm going to do the measurement using my attack code. I'm going to try to guess which website the victim is browsing to on this private browser. So, this is, I'm just going to show you the results with your eyes so you believe me. This is the output of memory consumption of memory accesses when three common websites are being loaded. So, on the top there is Facebook, and there is Google, and then there is Yahoo. This is the time axis. This is 5 seconds. And actually, black means there's a lot of memory activity in the cache, and white means there isn't so much. So you see, on the left, you actually see keystrokes. If you can count, you can see that Google has 6 and Facebook has so much. So every time there's keystrokes, there's activity. And then there is a big bunch of action when the stuff is coming from the network. And what you see here, actually, is the cursor. So when you go to Facebook, you have a cursor which blinks twice a second. So you can actually see there's a 2 Hertz signal here. And Google had when I was doing the measurement, they had this, this silly animation about, I don't know, it was something about the moon, or I don't know. So there was like a 30 frame per second animation, so it was a 30 frame per second signal. So with our eyes, we can tell apart these 3 different websites. So we tried to teach a computer to tell apart these websites. And this is, I'm not sure you can see this from the back, but 8 most common websites on the internet, according to Alexa. And we can detect with 90% accuracy what the victim is using, even if he's going through this super secure Tor browser using this attack. So it's really nice. And the natural question you asked is, there are more than 8 websites on the internet, right? Even if you take only the most common ones, maybe 10,000, 100,000 websites. So why don't you do that? Why didn't you measure 10,000 websites? And my answer to that is, please join my research group. This is something I want somebody to do. If you know Selenium, I'd really appreciate your help. So, this is an attack, and really nice. And one thing I want to mention is that I did some responsible disclosure, of course. This is white hat place, so reported it to March for Apple, Microsoft, Google, Mozilla. And the reason I'm not showing you a live demo is that actually, as of most of the versions of the browser which are shipping right now have really reduced the timing resolutions of the JavaScript timer. It used to be nanoseconds, now it's 5 microseconds. And it's still good enough for games and music and all sorts of stuff like that, but for our attack it's not enough. The problem, and of course, future APIs of JavaScript like shared array buffers are going to be also modified so you won't have this sensitive timing leak. But the problem is that this fix is really a band-aid. We only made JavaScript stop measuring time very sensitively. There's still Pinnacle and Flash and I don't know what else, Java and ActiveX, whatever. So the problem is still there, and the fix will have to come from the CPU designers. There's something called Intel CATS technology, which might be able to solve this, but it's not really out yet. It takes a long time to ship stuff in the hardware world. So, what did we see here? So, we saw a side-channel attack. Side-channel attacks are very well known, but they weren't really thought to be important to most people. So now we see you can actually get a computer connected to the web and victimize it using side-channel attack. And what really is special here also that we didn't compromise keys, but privacy. Another thing we can compromise is we can detect mouse motions, we can detect network accesses, and so on. So we really have to think about how do we protect against this kind of attack. And what's really important, the takeaway point is that many more systems and secure PC software have to be designed thinking about side-channel attacks. Even if you're writing a web application, I think you have to think about how can I protect myself from side-channel attacks from a neighboring web application. So it's very interesting, and really the question of who writes in the countermeasures, it's also a question, why should it be my problem that the CPU is designed this way? Shouldn't the operating system fix it somehow? Shouldn't the web browsers fix it somehow? Very interesting question. So, this is what I have to tell you today. We're very good on time. If you're interested in more information, please go to this website. This is a cache attack. 50 cents of attacking cache by eating it. And please, if this is interesting for you, please be in touch with me or with Batel outside. I have a lot of other interesting stuff to do. שאלות בעברית אני אתרגם. בבקשה.
Aren't the graphs very specific to each chip architecture?
Okay, the question is, are the graphs very specific to chip architecture? So actually, we think that the pictures I'm showing you are the composer, the browser composing the website. So every time there's something changing on the website, maybe a little browser or a little animation, there's a lot of memory moving across and I can detect it. So it's not the CPU, it's the website. So definitely different CPUs on the same website in the same network conditions will be very similar. What I can tell you is two different versions of browsers going to the same website or the same website one day after the other or in two different locations in the world. This is something I don't really know. But what I'm seeing here is the browser composing the website. So it's not really CPU dependent. Yes, sure.
What is the mitigation of this kind of attack? How do I protect myself?
Okay, so this attack needs a lot of, the question is how do I mitigate? So a lot of things are going on so this attack can succeed. First of all, the CPU is designed in a certain way, the OS is designed in a certain way, the browser is designed in a certain way, and JavaScript is designed in a certain way. So I can kind of break this chain in a lot of different locations. I can try making the API the browser gets much more limited. I can try writing the browser so that the way it composes to the screen is kind of sensitive to side-channel attacks, and I can write the operating system so this attack won't succeed. I can try to design the kernels in a special way, and I can write the CPUs so that sensitive applications get their own piece of the cache, which isn't shared with anybody. Each one of these approaches is reasonable. What we did right now is we put it on the browser because the browser guys are the most responsive, and they're the fastest ones to shoot a countermeasure. Yes? So the question is, what is my CPU consumption? It's about 10%. It's basically what I'm doing is I'm accessing a linked list and measuring how long it took me to access this linked list. So it's not very sensitive, not very high CPU consumption. Especially if I don't have to measure every 50 microseconds. I have to do this measurements once every millisecond. So you can imagine it's not very CPU intensive. Another one? Yes.
What if adding some random functionality to the site actually break the entire pattern?
Yes, so you're asking, can I use some kind of random functionality on the website to break this pattern? And the answer is yes. There are, as I said, side-channel attacks have been in the business for many decades in the more high-sensitive, aerospace and military and banking and so on. And there is a known art of how do I protect myself against side-channel attacks. You can use mitigation using randomness, you can use masking, you can use special kind of crypto and special kind of math. Yes, but the thing is that nobody actually thought of bothering to do it because they thought side-channel attacks are not relevant here. So yes, now we have to start thinking about it. Yes. Yes, Krishan.
How is it possible to monitor code action on this attack?
Yes. The question is, can I do keylogging? And the answer is yes. So I was actually, I got keystrokes. Okay, keys down and keys up. Actually, I was able even to measure when somebody was putting her finger on the mouse pad, not moving it. So even if you touch the mouse pad, I could get this measurement. And somebody else has been doing cache attacks, and they've been actually been able to find out not that you're typing, but actually what keys you're typing.
What is the difference if I type in general?
Okay, so what happens is that when you type something on screen, the operating system goes and draws the letters on the screen. And it takes the letter forms, the bitmaps, from a big array it has in memory. So the different addresses it goes to fetch A, B, C, and so on, you can detect that using cache attack. So you can actually find out the keystrokes. The challenge is, how do I teach my classifier to do this activity? So the really question is, how do I build the attack? Once the attack is there, you can do keylogging. Yes. One last question, maybe? Question? Okay, so for this specific attack to work, I need the cache to be inclusive. Inclusive means that if I throw something from the lowest level of the cache, it gets evicted from all the way up. So AMD is sometimes inclusive, sometimes exclusive. ARM is also sometimes inclusive, sometimes exclusive. So I didn't try it on AMD and ARM. I think it's going to be harder, but it should still be possible if you do the right thing. And if you're lucky and you get to run on the same core as the victim, then obviously you can do it on any kind of microarchitecture. Okay? I think we're finished. So, thank you again.